helps streamline commercial real estate transactions, empowering millions of users to close more than $600 billion in deals and over $7 trillion in property value since 2015. But let me tell you, I am so excited to be at Crexi. Today, we're sharing with you some very interesting work that started a few months before I joined that I have the very great privilege to be working on and sharing with you all today. My colleagues Isaac and James Healy-Markovich, who y'all might have heard give a talk on Friday on harnessing open source solutions for generative AI, did most of the heavy lifting in partnership with 3 significant service providers, Amazon Web Services, Datadog, and the open source powerhouse Pulumi. Isaac and James co-wrote a blog with Marina Novikova at AWS detailing this work, which is the primary source for this presentation. And of course, a huge shout out to our VPs, Chris Smith and Mark Roden, who are both on staff here at the SCaLE conference. And of course, thanks to the rest of our Crexi leadership who helped make this possible. So, most presentations end with a demo. We're going to mix it up a little bit and do a quick demo first of our self-service infrastructure AI assistant. And then we'll kind of overview the problem, lay out our approach, and go into the details a little bit, then go back and re-demo the front end with a little better context. This really blew me away the first time that I saw it. I think you guys are really going to love it.
Awesome. Thank you so much, XPaul.
I forgot to switch the thing.
Okay, go for that. So while he's doing that, I am about to get a little silly, so bear with me. Before we go any further, in a world drowned in water. No, wait, sorry, that's not right. Imagine a world where data scientists can quickly and easily deploy open source models without having to submit a single ticket. Doesn't that sound better than Waterworld? I mean, that movie was terrible. And I mean, it's certainly more dry. Okay, yeah, we're back to that. Right, don't repeat yourself. Okay, let's move on. So introducing self-service infrastructure, an internal platform tool built off of Pulumi and utilizing YAML. Let's do a quick demo showcasing our AI helper. We'll stay high level for now and go deeper into it later. Thank you. So I actually built all of this during one of our hackathons at Crexi, and I'm stoked to show it off. Let's get right into it. So with this UI, we need to give it our infrastructure needs. And because this is a talk about open source models, we'll keep it around that. However, this SSI tool has a ton of additional functionality. So I want an ML pipeline with 3 models in it, A to B to C. Let's use TensorFlow and PyTorch and include Hugging Face transformers. So we're just going to go ahead and hit send on that. And of course, a live demo has never gone badly once. So don't worry, I'm definitely not. Give it just a minute here, yeah. So this is using GPT-4 on the back end. So as you can see, it generated a YAML spec. We're not going to go too in-depth into it now. We will later. But let's just quickly go over it. So I asked for 3 models, A, B, and C. I asked it to use PyTorch, TensorFlow, and Hugging Face transformers for each. As you can see, it did a couple different things here, but the main one I want to focus on is this depends on clause, right? So I asked it to go A to B to C. We should be processing our data in a model chain. So model C depends on B, which depends on A, and this will allow us to run inferencing in ordered steps, taking the result and sending it to the next model in the chain. This is really powerful when you tie it together with multiple open source models. So let's take a look at the results. Yeah, you can see here depends on models B to models A, and then here we have a depends on for S3 buckets. This basically means it's created a fake bucket example that we can store inputs in, and then it will send to the first model, which will then get processed throughout the pipeline. Awesome. So at a high level, this produces a YAML that we can pop into GitHub and deploy via GitHub Actions. I'm going to pass it back to XPaul and let him explain the context behind this, and we'll talk more during the second demo.
Okay, So our SSI suite is the foundation for our pipeline deployment process. The AI front end gives us something cool to show, and it helps our developers and data scientists get the infrastructure they need. Today we're going to talk about Crexi's implementation for managing the pipelines. To be clear, I'm not an author or even a budding expert on the libraries. I'm just helping enable the other engineers and scientists wield these tools and hopefully manage them a little better. So the background in the landscape is basically this. Our data science, data engineering, and data quality teams have to be able to play with whatever the flavor of the week is. Like, literally, QWQ came out like on Tuesday or something. You may have seen this image before. I first saw it in Villatelos's book, Effective Data Science Infrastructure, but it's also on the Metaflow website. Data science involves a variety of processes, but it usually begins at the top with modeling, training, experimentation, moving down to deployment to the cloud services, worrying about revision control, integration and testing later, and then eventually to provisioning, procurement, and data handling. The data scientists care a lot about the modeling and very, very little about the underpinning infrastructure. The progress is happening so fast. The data scientists are in super, super high demand. So companies are looking for success stories. How do we adopt a culture that supports data scientists and get out of their way? At the same time, the engineering departments, we need operational solutions that are flexible enough to integrate seamlessly with other systems, but still provide a path to automation. All these libraries and models that are maturing constantly. The need for results is dramatically increasing. It becomes ever more important to standardize, to optimize, and to automate the processes for developing, training, and deploying the models. So we've built a very powerful, very flexible framework, lets us put up some guardrails while staying highly customizable and scalable. Lets us deploy various machine learning models incredibly efficiently, adaptable enough to meet diverse and developing project requirements. Speaking of which, for this requirement, we had several important requirements. Number one of which, of course, was rapid dynamic deployment, whatever model is available. We needed rollbacks, regression tests. We needed to reduce the risk of human error and ensure consistency of the process with operational transparency. We needed flexible sources and destinations. We had a variety of inputs. The documents could be coming from email, they could be coming from uploads. And the outputs may need to go to visualization services, to the data warehouse. And we needed, of course, standards and best practices. We needed observability, we needed monitoring, we needed to be able to detect the health and performance of the pipeline. And again, build reliable, efficient, scalable pipelines leveraged with confidence. So now we're going to deep dive into some of the implementation details. To build the system, we identified several technologies that we needed to use in order to also manage. First, we have Pulumi. This is a modern infrastructure as code tool. Similar to Terraform in that it can programmatically provision resources from a wide variety of service providers. It also resembles the AWS and Terraform CDKs in that it supports defining your own resource classes and logic wrappers in multiple software languages of your choice, in our case, TypeScript. One of the things we liked best about it is the native support for specs defined in the YAML format. Which offers three key advantages: increased efficiency. The data scientists can write and deploy their own models without having to learn a whole new configuration language. It's flexible, that they can customize the YAML to specify their own instance types, their model images, and additional permissions, optimizing for specific use cases. And of course, the YAML is simple, human readable, easier to understand than alternatives. Then we have the AWS resources that we're managing. We have The open telemetry collectors that we have collecting data, sending to Datadog integrations are both at the infra level as well as the Lambda level for logging, tracing, and resource performance. And finally, we leverage GitHub not just for centralized software version control, but also for their GitHub Action service, which allows us to execute our Pulumi scripts in that continuous CI/CD fashion I mentioned earlier. Allows the data scientists to perform new deploys or updates, preview any changes, and even destroy existing services using GitOps. Helps us keep the infrastructure reproducible and hardened against code regressions. Our system is designed in a modular approach. Each of the models that we have that are deployed on Amazon begin with a boilerplate Lambda function, basically triggered either by messages from the SNS or S3 object lambdas, which invoke calls to SageMaker endpoints that are custom configured to load from a model bucket and execute any inference logic asynchronously. When it's done, we can send out another SNS message for another Lambda or service to pick up, or direct the results to Kinesis Firehose or onto another S3 output bucket, which may then itself have another trigger to another Lambda. And because these are boilerplates, functions at the core, we can then link up a series of complex pipeline pathways directing the results anywhere we like, such as for consumption by our data warehouse, data lake, external systems for visualization, other business analysis, other applications on the platform. So one of our simple pipeline diagrams, I've called it a complex pipeline because it is complex in the sense that the diagram contains 3 models for 3 SageMaker endpoints, model A, B, and C. In this case, both model B and model C are dependent on the output from model A. The input to the pipeline starts when somebody drops an object into the input storage. It triggers the modular pipeline for model A, spins up the orchestration function, calls the model, drops the output into the model A output bucket, which then triggers 2 simultaneous calls to both B and C, and they start their own respective lambdas and write the output to their own storage bucket. And it should be clear by now that this is a highly extensible, very complex pipelines, no cap. Here we have one with 2 main lines, the top one and the bottom one. The first has 3 dependents, one of which continues onto a 3rd model in the chain. The second main line also has 3 chained models. Both of the 3 chains have a trigger for yet another model at the end. We've also included, for the purposes of this talk, a deliberately low-res screenshot of Datadog, where we've correlated our logged events from within the model pipelines. Well, we do have invocation metrics, including latency and processing times, failure counts, endpoint backlogs for all our known SageMaker models. We have a detailed view of the performance bottlenecks, as well as Lambda function monitoring. And now we also have OTel tracing to see events traced all the way through our pipelines. And lastly, we have a poor resolution screenshot of a manual workflow dispatch trigger against GitHub Action to deploy self-service infrastructure. On the left here, we have the listing of the recent executions of the workflow, which you can click on to see the details and the logs. On the right, we have the required inputs to invoke the workflow, including which version of the branch to invoke if you're doing it manually, whether to run it as a Pulumi up, a Pulumi preview, or Pulumi destroy, which environment to run it against, dev or prod, and path in the code base to where the YAML input file would be. The data scientists and developers keep their YAML files in their own repositories, and we have a shared GitHub action in the self-service repository that accepts calls from the development repositories using a consistent format, which can then be triggered against whatever triggers they need within their own autonomous SDLC process.
Awesome. Thank you so much, XPaul. It's so cool to see that workflow shown up there, as it took us a really long time to build it. So we're going to do another demo. We're just going to continue off of this last one. You mind holding this? So there are a couple things I want to show here. As I mentioned earlier, there's a lot more that this thing can do besides just spinning up what we call SageMaker pipelines, which are inferencing pipelines. And we'll show that as a part of this YAML. So there's a couple things here that it did placeholders for. We've got like the S3 path. So as some of you might know, there's a serving engine that hosts these models, but then you have to have an actual model artifact alongside that. So it created a default bucket with like a fake model artifact. And it also references for our initial input a fake bucket. So let's go ahead and have it, go ahead and create real buckets for our model artifacts and input to the pipeline. So what it should do is produce a new definition within this YAML file for S3 buckets specifically. Maybe one, maybe two, we'll see how it goes. And then after that, I'm going to be more specific about how we want to define that initial input. So right now, I think it's doing JSON files inside of the model A input folder on pipeline input bucket. So let's make sure it created pipeline input bucket first. So if we scroll down to the bottom here, here's our buckets section. You can see there's two buckets it created, model artifacts and then pipeline inputs. It added some additional readers. There's a lot behind the scenes that obviously isn't shown here, right? Like we don't touch on observability here. We don't touch on auto scaling, but under the hood, it's doing all of this via Pulumi and abstracting that away from the user and making it a lot easier to create these definitions with the best practices baked in. Now, as you can see, it's referencing the new S3 path that we created, model artifacts bucket for the artifacts. And then we've got our S3 bucket definition. So let's just have it do JSON. Instead of JSON, we'll do CSVs should be the input in the inputs directory. While that's doing that, I want to talk about what we're going to do next. So we have our buckets defined. We have our SageMaker pipelines. Let's talk about how we can process the data from the results of this inferencing pipeline, as well as create a Lambda to produce inputs. So we're going to create, first off, it did go ahead and create a CSV inputs directory. So it's looking for CSV files in the inputs directory, which is awesome. It did exactly what we wanted it to. Kept everything the same. Now let's go ahead and create two Lambdas. So one that processes the results of the pipeline, and another that will generate inputs and send them to our inputs bucket. Okay. And then after that, we'll have it deploy to prod, because as you can see right now, we're just working within our data dev environment, and we want to launch this thing into production right away. Let's not even test it. Hey, that's your guys' decision, right? We hand the keys to you if that's what you feel comfortable with. Okay, cool. So as you can see, there's also like an explanation that's defined with each one of these things and like a response of what it's doing. You can see here that we keep all of the model definition stuff the same. We have our model buckets, and then we have our Lambdas. So we support a bunch of different AWS services within self-service infrastructure, Lambdas being one of them. It generated a couple default placeholder pieces, like again for your bucket for the actual Lambda artifact. But as you can see here, the Lambda section itself has another depends on feature for SageMaker pipelines, which is what we define up here, right? That is pretty powerful because it means two things. One, not only can we have this depends on defined in the same YAML, but we can also define it in a different YAML. So if our data engineering team, for example, depends on this SageMaker pipeline infrastructure that we created for data science, they can just create a YAML, define depends on, and under the hood, it's going to create a Lambda that has triggers for every single one of the SNS topics that were generated for the SageMaker pipeline infrastructure. Now, there's two types of topics that are created usually. There's a success and a failures topic. If you guys have worked with asynchronous inferencing in SageMaker at all, that is super good to know because it will tell you if inferencing has failed. Yeah, so that's great. You can see some other just like placeholder things here, memory, timeout, how long before timeout occurs when making a request, the Python runtime, just cool stuff like that. And then we have a generates inputs lambda as well. And that is going to depend on the pipeline input bucket that we've defined as the depends on for Model A here. So what this means is what we showed earlier in the demo or in the slides. We have a full end-to-end pipeline working with lambdas producing an input, sending it to Model A completing inferencing, sending it to Model B and C, and then we have a lambda that listens in on every single one of those models and processes the results individually, both for successes and failures. So this is super cool. In minutes, we've basically created a complex ML pipeline. They could pop this into GitHub Actions and run it and deploy all the infrastructure they require. And the last piece I promised was, let's deploy this to prod. And it'll go through and create basically a duplication of the code. We have noticed one little issue where it will create the same buckets multiple times. And if any of you are familiar with AWS buckets, they are hosted in a global namespace. So we might need to modify that. In the end, there are some things that will need to be replaced by the user, but this gives us an amazing template to work from. And it also prevents them from having to manually define all of this stuff, look through the documentation in our self-service repo. There's a lot of advantages to doing it this way. Okay, so, oh gosh, there we go. As you can see, there's a prod environment now and a dev environment. So we have basically all of the same infrastructure, which is great. And let's see. Oh, no, look at that. It actually got the bucket names right. So it created different versions for prod specifically. Super cool. So does anybody real quick have any other AWS infrastructure they want to see if it can stand up? Anything? RDS. Actually, well, let's see. How about this? Does SSI support RDS? So it has complete knowledge of our self-service infrastructure platform and everything it supports. And the current JSON schema provided does not include a direct reference or support for our Amazon RDS. I think we do have Elasticache in there currently. Yeah, we have Elasticache. Elasticsearch, but and as that goes, it will let us know. And we could, yeah, so it does. Elasticsearch, open search serverless collection definition. So we could have it go ahead and create one. I'm not going to give it anything beyond that. Let's see what it comes up with. We haven't seen it yet either, but what's cool about this application that we've created is it has native error checking. So if it produces a YAML that doesn't complete or doesn't work with our schema, then it will see that there was a problem, we send the error back to it, and it will automatically fix itself. It's usually right the first time, but I bet if we did something super complex, we'd see some potential issues there. And look at that, open search serverless collection with different readers and security groups it's created and all sorts of cool stuff. So there's a lot of automation happening behind the scenes here, and it enables our data scientists to build very quickly with a high level of velocity. All right, passing it back to Expo. We just got to swap our display settings here real quick.
Yep, so we went through this pretty fast. So that's pretty much our project and our presentation. The ML pipeline framework that we've explored is robust, scalable, highly customizable, addresses all of Crexi's requirements. We can run experiments and try out new machine learning techniques at scale and with minimal hassle. We didn't really go into detail on the auto-scaling functions, but you can set the number of instances that you need for each of the endpoints with a minimum or a maximum or a constant value. We're able to separate the workflows, proactively monitor. We get seamless integration with our data lake, data warehouse by routing the outputs appropriately. That sort of interconnected ecosystem does more than improve current operations. It lays the groundwork for continuous innovation. The data warehouse serves as a rich resource for training new models, which can then also be deployed using these ML pipelines, enabling a virtuous cycle of improvement and experimentation that propels all of Crexi's projects forward. Do we have any questions?
Go ahead.
Hello. Well, first of all, thank you for the presentation. This is really interesting. Thank you both. I had two small questions. One is kind of technical and maybe it doesn't matter, but when you are generating this YAML, you mentioned both the GitHub Actions and the Pulumi part. Is this generating both?
Yeah, so the GitHub action utilizes Pulumi on the back end. Essentially, we have a Pulumi application called self-service that takes the YAML file, right? It takes all of the inputs that were provided in there and then, sends it to the application and does things with it. And GitHub Actions is basically the catalyst to start that process. GitHub Actions will take the YAML, put it inside of the process, run Pulumi up, and it will do its thing.
So the GitHub Actions in this case is just a thin layer and it's all done in Pulumi.
Correct. You could use other CI/CD systems if you want to do the same thing.
I know that Pulumi is a great tool, so it's not like I'm not doubting like that Pulumi is good, but like why choose Pulumi and let's say not use direct YAML from one of the other tools?
Yeah, that's a great question.
CloudFormation.
There's a lot of reasons why you would go back and forth. I'm probably not going to debate the specifics between, but I will say I've been using Pulumi for about 5 or 6 years now. I'm really passionate about it because it allows us to build infrastructure as code using our native languages. I think at the time we built this, it was before the Terraform CDK came out. And personally, I just don't enjoy the rigidness that Terraform has. Does that answer your question? Yeah, we can argue later.
So I actually don't know a lot about how this like GPT tool works. Did you guys just I don't know, plug all of the definitions for all of these things into like the context that you throw like up to OpenAI or whoever is using whoever we're using for that?
Sure. Yeah, so it is using ChatGPT on the back end. We created this during a hackathon, and the goal was to basically give it full knowledge of the user inputs and all of the kind of readmes and descriptions around them. So instead of having to come to like DevOps for help with anything relating to SSI, they can use, and I mean this has happened so many times, they can use a self-service infrastructure bot to get their questions answered and produce those YAMLs. But yes, to answer your question, it's essentially Pulumi application is what generates the actual infrastructure as code. Self-service GPT is another service we have running that has access to our schema definition for our YAML. And then we do a lot of commentary and descriptions within our schema. And since the AI can read that, it's able to use those to generate code successfully. And then like I mentioned earlier, there's error checking. So it allows us to basically say, hey, was the YAML that you produced something that will actually run when it executes inside of the GitHub action? And that's great. I think it has like a maximum of like 5 error checks. So it'll go like, did this work? No, did this work? Did this work? But it's never gotten past like 1, which is pretty great. And as new GPT versions evolve, we'll probably look into something a little bit smaller to make it a little more responsive. But I will say the speed of this is vastly superior to asynchronous communications with DevOps or anything like that.
That's very cool. Thanks.
Yeah. Thank you. Anybody else?
So you touched on error handling. One of the challenges that I've certainly seen a number of times is infrastructure might sometimes time out on trying to provision a particular resource, and now you've got it partway into a state. And how do I roll that back, or if I run it again, and maybe I'm actually going to get a different result because I'm partially provisioned. How do you handle that? And then a second part would be sometimes infrastructure providers change definitions on a regular basis, so I can imagine you might be based on one particular version and another version comes out. How have you handled those couple things?
Yeah, so I'll answer the second question first. We pin to specific versions of Pulumi providers, which are going to define how cloud infrastructure is defined within Pulumi, right? So that helps us on that side, because it's not going to, AWS versions their APIs, so they're not going to produce changes that are going to break our existing stuff, which is cool. I like that a lot. Now, when it's time to upgrade, we just go through, update our packages. We do diffs to see if anything's broken. There's some automated unit testing and integration testing, unit testing. I want to get integration testing in there, but right now we're focused on some pre-built tests we created. So hopefully that answers the second question. As for the first, how do you prevent failures midway through from destroying everything? And the truth is, on first run, if something breaks pretty heavily and this isn't in production, I'll probably just have them destroy the stack and recreate it. I've seen this mainly two ways. So when a SageMaker endpoint is standing up and the model artifact under the hood is like bad code, you won't see it, unfortunately, until it fully tries to deploy the endpoint. In that case, AWS has some weird thing where you have to delete the endpoint first and then try to redeploy it. So that's a bit of a manual process. I would like to improve on that. The second piece is we do have a bunch of checks within our code itself to be like, was this thing created? If not, don't continue. There's specifically within Pulumi the ability to depend on another resource. So to create my ECS or my Lambda function, I need the bucket that stores the Lambda artifact to exist first. So it's that order of operations that kind of helps us. So one thing will fail at a time, most of the time, unless we have a bunch of asynchronous work happening. And you just kind of work your code around that. We had to do a bunch of that for our service deploy specifically, not so much with the SageMaker stuff. Does that answer your question?
We have had like the occasional incident where we had to go in and manually invoke Pulumi on the command line and figure out what went wrong with the deployment. I think specifically we had some IAM policies where the roles had been deleted and Pulumi was trying to refresh and got invalid policy identifiers, and there was nothing that could be done from the GitHub action where we actually had to go in manually, make the changes, and update Pulumi appropriately. But that's like so very far and few between in terms of the number of operations that are being called by the development teams to deploy new services or to update the existing ones. So,
yeah, just like Pulumi, or just like Terraform, there's a state file you can modify. So if you need to true things up and Pulumi refresh is broken for something like a policy being destroyed due to some weird AWS behavior, you're able to just manually remediate it. But like XPaul said, that's actually really rare. We don't have it happen very often.
Yeah, I guess I'd add on, from my perspective, it might be relatively rare on AWS. I've seen other cloud service providers that have resource timeouts and that sort of things. AWS certainly occasionally has these kinds of things, but then it leaves you in this kind of like semi-broken state, and how do you roll forward? So that was kind of the context for the question.
When we're multi-cloud, I'll let you know. Anything else?
Hey, thanks for the talk. I was curious about the GitHub Actions integration. Are these GitHub Actions just generated as part of these prompts and then run all the Pulumi actions for you? And if so, if I understand that correctly, are you using Pulumi deployments for this?
Great question. They are not dynamically created. We have a generic baseline script that we can add to a new repo really quickly. There's some like tokens we need to allow it to access as well as a part of the script. So, hey, I just built this new repo DevOps. Can you help us get it ready for self-service infrastructure? So there is a step that requires a ticket to get a repo initiated. And there's some really cool stuff we can do to maybe remediate that, specifically around Pulumi's automation CDK, which basically allows you to control stack creation. You seem familiar.
Disclaimer, I work there.
oh,
I love you guys.
Yeah.
I love you guys so much. Okay. Well, thank you. Yeah, I do want to introduce that tool. There's so much really cool stuff that you can do with it.
Yeah, it's curious. Thank you.
Thank you. Awesome.
Anyone else? Going once, going twice?
So Crexi is a real estate exchange, correct? So
Yeah.
how do you foresee using this for, like, your company?
That's a good question. I'm not sure how specific I can get with the answer.
Trade secrets.
We had our slides heavily reviewed by our legal department to make sure that we weren't disclosing anything too proprietary. But one can imagine in a real estate transaction, specifically in a commercial real estate transaction, there are things that you want to know about a property or a listing. Maybe there are brochures, maybe there are documents that would be interesting to be able to programmatically retrieve data from. Once you have access to that data, there are a lot more interesting things that can be done upon it. Did I answer that question?
Assumption is pulling environmental data to see how much you should be paying for it or not pay for it, or how much your rent should be, or things like that, right? Generating some kind of information for you guys. No,
Yeah.
not at all.
Yeah, you can ask those two. They have some.
We do not set or recommend or do anything with pricing. We are staying very far away from that. There is a lot of ongoing litigation in the multifamily space that we have zero desire to be touching whatsoever. We released a product last year called the Lease Data Initiative, and so that was publicly released. We actually had a whole launch for that, so I think we can talk about that in public since we launched it. And this infrastructure served as a foundation for gathering that lease data information.
I will say our pipeline has gotten up to like 20 models or something like that at this point. It's really big, and so the flexibility has helped us a lot with kind of being able to improve and adapt to different situations as we've grown. Self-service ML pipelines at the beginning were much different than where we are today. So, awesome. Well, thank you guys so much.
Yeah,
appreciate everybody coming out.
And thanks to SCaLE for hosting us. This was a lot of fun.
Cool. Thank you, Crexi people.
Woohoo! I know. Let me turn the thing off.
Hello, hello. Hello, 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 hello. I think that. Hello, hello. Alrighty. All right, so this is Beyond Replication, a holistic approach to application scaling. Thank you for joining. My name is Josh Thornton. I'm a founding engineer at SCaLE. I wrote and maintain the world's most realistic load generator and mock server. At SCaLE, we kind of work with network traffic that we capture and then use that for load generators and mock servers. So part of my job is interacting with customers and helping them scale up their applications. And regularly as part of my job, I'm evaluating both our internal applications as we grow, so we're a startup, and the customers who use our tools to scale their own applications. So in this talk, you'll learn how to approach a problem of scaling your application, when you should look at things like that, tools for diagnosing issues, pitfalls to avoid. We're going to look at a few Go p-profs, and we'll go deep on some things, but we're really going to skim the surface of this area because we don't have 12 hours here, and performance tuning is kind of a big topic. So when I talk about application scaling, usually we're talking about response time, so the amount of time between when a customer requests something from your application, when they get an answer, and the total throughput, so how many of those customers doing the same thing you can handle at the same time. And usually in the talk, when I say application, I mean like a single process that you're running, and I'll use the word system to talk about your entire set of services that make up the external service that customers interact with. So really, why do we care about this? If your application is not performant or doesn't scale well, your customers are going to get errors or slow response times. If your app is public, you'll be dropped down on SEO, and you won't be bringing people in as much. So realistically, the answer is money. And if you can provide a better experience to your customers, then you are more valuable to your organization, and they will pay you more. That's also about money. There's also something, if you've been on Hacker News, you may have heard of the hug of death. So this is where on Hacker News, you have a post about your company, it rises to the top, and potentially tens of thousands of people are trying to access your service and your site and sign up, and that's really the time when you need to scale. Those people, if it doesn't work the first time, they're not coming back, right? So you need to be ready. So where do I start is a question that we want to address here. There's so many ways to address scaling, a million things to look at, and a million ways to approach it. At a high level, you want to be ready before you need to be ready. Okay, so load tends to come unannounced, like we said with the Hacker News hug of death. You need monitoring in place so you know what happens. You don't want your customer to tell you that your application isn't scaling or that they have errors. You want to be able to see what's going on, and you really want an internal view. You want runbooks. If you're having a problem with your application and you need to go to the next level, that's already a hard enough problem, so make the easy things easy. Scaling your apps, resizing volumes, have runbooks to make sure you can move through these quickly. Understanding scalable patterns would be application patterns, architectural patterns for doing these. There's a ton of good books for that. And really load testing ahead of time, and load testing ideally, or detecting load regressions in CI and CD before you deploy is critical, because these things rarely show up in dev, right? Like if you have a performance issue, you're not going to notice on the app running on your laptop. You're going to notice when you have 1,000 people looking at it. So the part of the talk is beyond replication. So replication is more servers, or just bigger servers, bigger nodes. So this generally doesn't work because your code may be inefficient, which may scale properly, but will cost a lot more money long term. A slow third party, so if your app scales properly, but a downstream service, either that your company owns and runs, or something that you're talking to doesn't scale, can be an issue. Of course, there's architectural constraints. Maybe you really need a time series database and you're using something transactional, it doesn't really fit your model, that's gonna slow you down. But the biggest thing overall are synchronization bottlenecks. So this is coordination either within an application, within a process, or across processes. This is what I see a lot. So databases have even dropped down to table and row level locks, but if you're accessing the same thing, or if you're accessing a shared key and a cache that's being rewritten and read, it's going to slow things down. Or heaven forbid, a centralized coordination among processes. So this is really the graph that you want for scaling your app. This is what a blog looks like. Okay, so medium.com has, they have bigger stuff, CDNs and caches, but they add more nodes. You're serving static assets, and so you get a higher throughput from adding those resources. Unfortunately, most applications don't work this way, right? You've got some sort of coordination in the middle that's going to slow things down, and just adding nodes, while it may get you a little higher, is not really going to get you there. Also, this little dip at the end on my highly detailed graph here shows what generally happens when you start really utilizing your resources. Things tend to get shaky because at full utilization, everything gets unpredictable. You'll see big bursts of throughput and then big drops. So we've got a cycle here that can tell us how to analyze and try and deal with these things. So first we evaluate, is it good enough now, right? We measure because we want data-driven decision making. We never want to guess about these things. We want to analyze, taking all the data that we have and actually figuring out what's going on, which is usually the hardest problem. This is why humans are involved, and LLM isn't going to solve this part of the problem for you. And then we have to implement and change the system in an effective way. And importantly, once it's fast enough, stop. If you've never optimized an application or a system before, you'll get a big boost up front, and then you will spend forever trying to eke out the little changes near the end. And only you know when it's fast enough. So your system is a unique butterfly. Now, some parts of your system realistically will have known solutions. If my database is running slow and I need to add an index, then for MySQL or Postgres, you can look at that and there's a known solution to that problem. But your system as a whole is a combination of all different kinds of implementation decisions, and only you can really tell when your system is good enough, when it's fast enough. So you have a 5-second response time. Is that too much? If you're an e-commerce website, then yeah, that's a lot, that's too much. Are you generating a report for 3 months of data? 5 seconds is probably fine, right? It's important to consider your access patterns and your customers, and always measure your results at the customer level, what the customer is seeing, right? Not some little interaction between your process that got a little faster, but what does the customer actually see? So if we're looking at the measure part of the cycle, we want to care about metrics like throughput rate, so how many services or how many requests are going through my system at one time. Errors, very important to consider errors because errors are often the fastest. Okay, so if your application is making a database request and it gets all the way through and does some database processing, that's a lot slower than the database isn't ready and I get a 500. So you start spitting errors, it's going to look like your throughput went way up, but it's not what you want to see. Latency duration is how long these requests are going to take, measuring that as a whole, but also for particular operations. And then saturation for things that you can measure. This is 100% of what my system can handle. How close to that am I? Which is going to change how you look at things. And you can reference the read and use methods are good systems to look at this. When you're looking at these, anomalies are very important. So if you're looking at a graph of throughput or latency and you see a big spike or a big drop, those things may be really short in time, but can often indicate a deeper problem and it can often tell you where to look. So don't just write those off. And then it's super important to care about tail latency. So the P99 is the requests that are slower than 99% of the other ones. And the P999 is the 99.9 percentile slowest request. And these are often a very small fraction of the requests you have, but they're usually the most important because who is utilizing your system the most? Who has the most data and the biggest database tables? Those are the customers that are paying you the most. Those are the ones that you want to care about the most. So tools to use are simple metrics. These are great because they're easy to implement and understand. They're tailored to your specific need. You know, when you put in a very specific metric, there's no wondering about what that tells you. You know exactly what it is. And not just for overall latency, but you can even, you know, track very specific things within your application. These will definitely come in handy later when you need them. There's also built-in metrics. So these are for RDS. Many of the tools you use already export metrics, so they're there. You should use them. And usually in the observability space, you have metrics, logs, and traces. Logs won't help us as much in this case. Traces may. Traces will tell you essentially across your whole system. It'll help you narrow down into what's causing the issue. But the problem with traces often is that if you don't have tracing everywhere, it's a lot less valuable, right? If you have a chain of, you know, 5 services and one in the middle doesn't propagate your traces, then you're not going to get the information you need. And in larger companies with more services, this can be hard to get adoption. In the measuring tools, we have load testing tools. So SpeedScale makes a load testing tool. That's me. But also there's JMeter and there's Vegeta, and you can use K6. And there's actually like a ton of these, probably because it's easy to write a basic load generator. You know, you're just sending requests at your service. But the important part is to use realistic load. Okay, so look, I've written the load test for your service here. This is a K6 load test. We have 100 virtual users. We run 100,000 iterations, and we hit your health check endpoint and see if it returns a 200, right? So we're done. That's all we need to do. But the problem is you're not really testing the system, right? How many API endpoints, how many endpoints does your API have? How many permutations are there in total? Because one endpoint, like the get orders endpoint, may have some differing logic based on what the user is requesting. And getting a realistic sample when you're trying to test your application to make sure it can handle higher load is critically important. So we use Go at SpeedScale, and so I'm familiar with looking at pprofs. There's also, you know, other profiling tools for other languages. There's Visual VM for Java. There's several profilers for Rust. Intel vTune is good if you want to look at very specific information about your CPU and see how it's you know, handling cache data. And if we look at this profile here, this is from an error that we discovered where we had a large loop that was adding fields to a logger recursively in the loop, right? So every time we ran the loop, it would add the same fields to the logger over and over, and the program crashed because 85% of the memory was being used for log fields, right? Here's another one. This one's actually a lot more obvious, points to one place where everything is going through a single mutex. Down there at the bottom, that's our biggest block, and 83% of the mutex time is going through this single mutex. So these pprofs will really help you narrow down when you're looking at performance within a particular process or application. This is the Go execution tracer, another Go specific tool, but can give you really detailed information. The execution tracer has a high learning curve, but can give you really detailed information. So in this case, all the little lines in the middle is small tasks being shifted between Go routines, and we could see, things are generally going along well, and these two big blocks on the side is where nothing at all is happening, and it's waiting for this net.sysdialer.dial. And what's happening in this case is we're waiting for network connections. So this was an improper reuse of network connections in an application that uses them a lot. And we would create tens of thousands of sockets in use. Those were being closed but sit open in a time wait state, which hangs around waiting for delayed packets to come in when one side of the connection is closed. Ran out of file descriptors, and so we have the application just sitting here waiting to dial on all CPUs. Grafana is here at the conference, and they maintain this tool called Pyroscope, which is pretty good. Pyroscope is multi-language. Also does continuous profiling and gives you a diff between profiles, so that's pretty handy. And newer versions, I'm told, will give you an AI text-based description of your profile if you're into that sort of thing. BPF trace, there's been a couple of talks on this. You can go really deep into kernel level visibility. This is super powerful. It's probably not what you need. This stuff is really interesting to go down and look at, optimizing the TCP stack, but realistically, unless you're at a FANG company, you haven't already optimized your system in bigger ways, and there are ways to, reduce the amount of work you're doing by 10x. It's important to measure before you need it. Like I said, you'll almost never find these issues on your laptop or in dev. You'll find them in prod. So you can do the continuous profiling like we saw with Pyroscope. We have a way to do on-demand profiling, so I can send a signal and create a profile if something is not looking right and generate that. And you can also do this in CI/CD. So validating performance requirements alongside other tests is something that more mature organizations will do because they're the ones that have hit these problems before. They've released things and either introduced a regression to where now you are at a certain performance level, you're higher, and your current infrastructure cannot handle it, or you just get a bunch more users and you need to make sure that you're able to handle that sort of load. Then we move on to the analysis phase, where we want to identify the bottleneck and take all the data and information that we've collected and use it to determine what our problem is. This is often the hardest part of the process. Sometimes your app is just doing a lot. Again, usually not. If you haven't really dug into this stuff before, there's often a lot of things that you can optimize, but it's difficult because it can require looking at everything depending on the scope of the problem and where you find it. The scope of the problem may be your entire system, and that could be really hard to narrow down. So again, having those measurements ahead of time will help you get there. So just like any issue that you're dealing with, problem that you're trying to solve, really understanding the problem is core. being able to recreate it locally, and only targeting the spot where the issue is really occurring, you can spend a ton of time optimizing things that look inefficient that won't actually make your app faster. I've done a bunch of that, and but it's not going to get you there. So really making sure you understand these tools is important. Which brings me to the next point, which is looking at this before you need to. If the first time you look at these performance metrics is when you're having a problem, or heaven forbid, the first time you try to create them when you're having a problem, you're not really going to be prepared. If the first time you look at a profiling tool is the first time when you're having an issue, then you're not going to know what bad looks like. So you can't, you can't fix the problem because you don't know what it looks like when it's good, right? The first time you open the hood of your car is when something's broken. You're not going to know what to fix. It's also important to ask for help, talk to your communities. This is small text, but me asking someone in the Go community, in the performance channel, hey, look at this pprof and help me out. They say, it looks like there are a ton of timers in your app firing very often. And I said, wow, my app is creating a disturbing number of timers, not reusing them, and it was causing an issue. And this is the pprof of that. So we've got the runtime.runtimer, runtime run one timer, and the sift down timer. The word timer's in there a lot, obviously in retrospect, but I didn't really know what I was looking for. These are all internal Go methods, not things in my code. So when you get to the implementation phase and you want to change the system, it's helpful with like any other problem to make the smallest change possible to validate your assumptions. Follow the scientific method. Don't be gentle. I think often we make a fix and then you say, hey, I've been running this one little test, this one little check to see if my fix worked, right? And once that passes, I'm done. But then you go and release it and somebody's going to use it in a different way. So try to break them and just avoid complexity everywhere you can. Complex systems are harder to understand, debug, change, and these problems can be hard enough already. You don't want to be dealing with spaghetti code or a spaghetti interaction between components when you're trying to analyze the performance of the system. And then you do it again, right? It's very unlikely you will solve this on the first round. I would say try and learn it every step and keep notes because the problem space can be large. There's a couple of generalized strategies for this. First, there's configuration. So these are, there's more and faster hardware. There's database indexes. Your runtime generally has ways to tune the garbage collector. Go has a Go max proc setting to avoid CPU contention. Java has a ton of flags for this sort of stuff. Your operating system has ulimits and network stack tuning, and if you're in Kubernetes or some other platform, there's a ton of stuff there. And those are the easiest to change. Those are the ones that you can flip a switch and get something out of it. Beyond that, there's in-application, which might be caching, avoiding sending data over the network. Predictive preloading is, I know my customer might need this. I'm going to spend a little time and effort. This would be reducing latency within your application. Retry with backoff. You don't want to run through a 15-step process inside your app or multiple apps and then die in the middle because one of your services was unavailable for a second. So there's also architectural patterns. Hopefully this is not what you need because these are the hardest to change, right? These are going to be potentially multi-week, month efforts with a lot of meetings in between. But getting closer to the client would be like a CDN or edge computing. The circuit breaker pattern will let you avoid going further if there are errors. So that will generally return a good response to some users and a bad response to other users faster rather than everybody waiting longer to get a bad response. Pull-based architectures can work well here because if I'm sending a ton of requests at a synchronous API and it has to respond right now or it dies, then under load it might die. So having servers that can pull from a queue and do the work as fast as possible will better utilize those resources. Reduced hops between services and stateless services make scaling, horizontal scaling, a lot easier. And we talked a little bit about continuous performance testing earlier, right? So this is where I might have my application in CI or CD, and I say, you know, I really want to do a performance test on my app before it gets released out to production so that I can detect these issues. And this is really easy. You have your app, and just like you would run a set of tests against your app, you just take a load balancer, or a load generator, excuse me, stick it in front of your app, and send it a bunch of load. Although I did forget that now that you're sending load at your app, real network traffic, it's going to try and access information in the database. And this is in our shared environment here, but that's where all our data is. I don't really want that because somebody's going to delete my table or change things, and it's not going to be hard to replicate. So I'll just move that into my pipeline. But now I forgot I need data in there. But I could just add data, store some, you know, I'll preload it with the data that I need. I also forgot that there are other APIs that I need to talk to, and those APIs have their own databases and APIs, and some of these may be external, which is outside of your control. So maybe this is not as easy as we thought, but there is a way that we can get here. So if we have our app and a load generator, we can back our app with mocks. So people feel differently towards mocks, especially in like a unit testing context, because a mock isn't necessarily the real thing. And when people write mocks, they make assumptions and they code their assumptions into the mocks. But for any sufficiently complex system, mocks are really the simplest way to create a reproducible environment. And the alternative to this is kind of like an ephemeral environment where it stands up all the other dependencies, but I wouldn't expect that to be cheap or easy to implement, and then you still have third parties that are outside of your control. I would recommend, you know, if you're using mocks like this, there are several tools that can take real traffic and create mocks from it. That's my preferred method because you really do want something that's as close as possible to the real thing. And then once you've set up mocks, you can create a subsystem where you group a number of applications, a part of your system in there, and use the mock server, and then test performance through those, getting real verified requests in and out without a lot of the extra complexity. And that's it. Thank you. Yeah, anybody have questions I can answer? No? Thanks a lot.